So now we are going to be discussing about computer vision fundamentals. So let's take this like this. We are going to understand how images are represented when it comes to computer vision. So let's take an image. Let's take this. Let's take a line. Let's take this. No, this is wrong. Let's take this. No, let's take another line. Let's take this, a new line. Let's take this. Stop here. So let's assume that this is our image, and let's assume that image are in pixel. Let's assume that this is 640 by 640 pixels. So let's take this 640 by 640. 640. Now we need to understand that a pixel is like, let's take these little boxes here as pixels. We need to understand that a pixel is like a representation of three main colors: red, green, and blue. So, and each pixel is represented by the three colors. And we have to understand now what that means is that for each and every pixel, let's say we have three colors here. Three colors. Let me just take boxes. Boxes should make it this easier. Rectangle. Let's say we have a rectangle here. Let's say we duplicate this. Another rectangle. Duplicate. Another rectangle. Duplicate, yes. Oh, I should have made this bigger, but that works. Let's still proceed. So let's assume that each pixel are represented by three colors. Let's take this as red. Let's take this as green. Let's take this as blue. So from this representation, right, we need to understand that it means even though we have this, the amount of pixels we are going to have in this image, the amount of pixel we are going to have in this image means total pixel count. Let's put this here. Total pixel count is equal to 640 times 640. So that should be about 409,600 pixels. But we are taking it as an example that each of these boxes is a pixel. So to represent this now, the pixel is a single location in an image, as you can see here. So, and that means we should have about 409,600 pixels in this picture. So, and each pixel needs three numbers to describe its color. So we need to understand that each of these colors, they are represented by an intensity of 0 to 255. 0 to 255. No. Let's correct this. Also this 0, what's happening? 0 to 255. So from this intuition now, it means for each and every one of these pixels, we need to have a number that represents the intensity of red, number that represents intensity of green, and a number that represents the intensity of blue. So what does that mean? The total amount of numbers for all this image would now be 3 for the amount of representation for each pixel times 640 times 640. So what does that mean? We'll be having a total of 1,228,800 numbers to represent a single image of 640 by 640 pixel. So to move forward with this, right? In PyTorch, this is how the images are represented. That means we have about 1.2 million numbers for the model to process for an image of 640 by 640 pixel. So you need to understand that when you give a model an image, it sees a tensor of numbers. So that means it's, instead of seeing the image as an image in this instance now, let's take this once again. Let's take a free. It sees it as something like this, but this is an intuition though. Let me undo this. Just a sample instead of that. So it sees that as a tensor of like one, let's say an intensity of 1, or an intensity of numbers really. This is not how it is, but just to provide us with like a sample. So it is a tensor of numbers, each representing the intensity of each one of these colors, right? This is not how it looks like, but this is just the intuition behind it. I don't want us to go too deep currently. So the model sees a tensor of numbers. The model learns which pattern of numbers correspond to which object. Each layer learn edges and colors. Middle layers learn shapes and texture. Late layers learn object level concepts like banana or grape. So we need to understand the difference between classification, object detection, and segmentation. So let's move on with this. So let's assume that I have, like, let's say frame. This is not what I want. Let's assume that I have, or let's say I have, let me put this here. Let's say I have a frame. I have to move this. Oh, no, this is wrong. Or let's just imagine that I have a box rather, so we don't make this complex. Let's set that. I have a box here, and I have a banana inside. Or let's say, where is an object? Object. No. Let's say I have a banana. This has to be bigger. Let's assume that this is an image now. Let me duplicate it. Duplicate. No, I have to duplicate the entire thing. Duplicate, also duplicate. So let's move on. So we are trying to understand the difference between classification, detection, and segmentation. So this is what classification means now. It means for this, let me label this classy. No, this is too short. This is too okay. Classification. Let's give this as okay. So this is how this works, right? So for classification, you can only have one single label. So when you provide this image with banana to a classification model, it gives you a single label that this is a banana when you train the model. But what if you now have, like, let's say an apple here? And let's say you have like an apple here. And let's say you have like an apple here. So what happens is, if when you run this model, this image through the model for classification, it only sees this as a banana. And why I won't say sees it as a banana, but if the confidence threshold when it predicts this classification model, if the highest confidence threshold is banana, it will tell you that this is a banana, ignoring the apple completely. That's its classification. So it is either one thing or the other. Now, how this differs from detection or computer vision is that you would have trained your model with several labels. So, and what that means is that instead of the model seeing just banana, it gives you a list of predictions with boxes around them. So let me get this. Let me just get a free. So it does something like this, that okay, I saw a banana here, and it comes here and says I see an apple here. So it gives you two predictions. Yeah. Banana and apple. And it takes this a step further by providing you with what we call bounding boxes. But in this case, I'll just give it like an array of objects. For banana and for apple, just a sample as what we got from the model. But now this would be like a class label. Let's say banana is 0, right? And it gives you xywh. We don't need to think too deep about this. And let's say apple is 1, it also gives you xywh. So we would get to know more about this as we progress. But when it comes to segmentation now, it's just, how would I call it, mask. Let's say it detects a banana and the banana has the highest confidence. What it does is it takes a box, right, on this. No, this is wrong. Oh, I have to do this. I have to return this back to the way it was. So banana and apple, and it gives xywh 0, 1, 2, 3, 4. And it also has below 1, 3, 4, 5, 6. So we'll get to know more about these bounding boxes as we proceed. Again, when it comes to segmentation, what it does is it draws like, let's say the banana was the one with highest confidence, and it masks the entire thing. Let me fill it. Like, let's say, let me just take a pen and just fill it with completely, how would I say, dark stuff. Like, it just segments, it masks what it detects. It masks the entire thing. So it masks, it puts like a, how would I call it, ignore this rough work. It puts like a mask on the entire thing to make you know that, oh, something is here. It masks that pixel. in essence. So, but in this course, what we are doing is object detection, right? And to make this clearer again, classification detects one label per image, right? Simpler, no location. Object detection, this is where we are. It detects multiple objects plus their location. For segmentation, it just implements pixel level masks, which pixels belong to which fruit. Pixel per class map, yeah. So, and that makes us know that for this, right, to correct that intuition, even if it detects this, it would also mask it and also label it. Yeah, so it does not have to detect only one. So in some way, classification detects only one object per detection. Detection detects multiple objects, right, and gives you a location, while segmentation detects multiple objects too, but masks those objects based on their class. So let me tag this as segmentation. So we need to discuss about confidence scores and YOLO. But before that, we have to discuss about bounding box encoding. Like I said, when we would eventually get to see annotations, what we call bounding box encoding for YOLO formats. So it comes like this. Let's assume that you have a list of classes. Like let's use what we have in this project. We have, how would I call it? We have, what are the classes that we have once again? We have Apple. Let's take a text box. We have Apple. We have banana. Let me extend this. We have grapes. We have kiwi. We have mango. We have orange. So since, like we said, your model, your computer on a byte level, on a bit level, understands numbers. So what happens is in YOLO, let's assume that this is how we order our label, and we have to understand something. When doing annotation, when you are training a computer vision model, the layering or the ordering of your labels must be the same all through. So let's assume that Apple is 0. Since computer science, we have it as 0 index. So everything starts at 0, not 1. We have banana as 1. We have grapes as 2, label 2. We have kiwi as 3. We have mango as 4. We have orange as 5. So what does that mean? So let's now assume that I'm trying to annotate this image, right? So I take this, like you can see now, we have the class ID first, we have the X center next, we have the Y center next, we have the width next, and we have the height next. So let's assume that for our first, trying to annotate this, let's assume that for our first label, we label the banana. So a banana is what? Banana is our label for number 1. Let's assume that we now have our X center, Y center, width and height as 0.5. We have this as 0.7. We have this as 0.3, and we have this as 0.9. So even if we now have an apple in the same image, right, we can then now have this as 0. We might have this as 0.1 have this as 0.6, have this as 0.4, and have this as 0.8. Again, these are samples. So this is what we are going to have like in our annotation file for that specific image. So the class ID is the banana, matches the dataset.yaml that we are going to see. Like I said, ordering is very, very important in computer vision. We have the X center, which is the box center, which is 52% across the image width. Y center 0.38, box center is 38% down the image height. Width 0.31, box spans 31% of image width. Height is like 0.45, box that spans 45% of the image width. So that is how the ordering, right, looks like in when it comes to the box encoding. So as I said, right, we now have to talk about the confidence scores and the YOU. So let's assume that we have a banana. Let's come here again to pick up a banana. So let's say we have the banana here. So let's assume that this is the actual box for the banana. Let's assume that this is our actual annotation for the banana. And let's now assume that when we ran our model through this banana, it's predicted this banana, but it came up with this box instead. No. Let's assume that it came up with this box instead. So the IOU in this instance, which is the intersection over union, is when we have an IOU. Let's assume that our IOU is 1.0. That means it is perfect match. But if we look at this now, right, we would see that this predicted box, let me call this the predicted box. The predicted box. And this would be our annotation. No. Or our ground truth. We call it ground truth, but let me just use both names to make it easier for us to understand. Ground truth or actual box. And this would be our prediction or predicted box. So just looking at this roughly, we can say this capture, this predicted box is almost overlapping or almost the same as this, but we can say, looking at this roughly, we can call it like 60 or 70% overlapping. So in this case, our IOU would be about 0.7 or 70% in this case. So that is what intersection over union solves. So it is, in short, we call it IOU, intersection over union, one of the metrics for computer vision. So for confidence scores, the model outputs a confidence score from 0.1 for each detection. What does that mean? It means when the model predicts that, oh, I can find the banana here, it can tell me that for this banana is equal to banana. Okay, let me just extend this. It could say it is confident that this is 0.8% banana, or what, 80%. Let me extend this. And it could say this apple prediction, it could say it is about 0.4, right, which is what, 40%. So that is what the confidence score. So high confidence score more than 0.9 means the model is certain. Low confidence score, let's say 0.3 or 30%, the model is unsure. So we filter in inference pipeline for confidence score of 0.4. And the best way to define or determine your confidence score when you're building a production pipeline is you are going to test based on your test data. After training, after validation, after you have your metrics, you can then take that model and predict on several new images. You could find that, oh, you were able to reduce false positives by setting your confidence score at 0.95. In cases where a false positive is going to be too expensive for the company, or let's say in cases of medical imaging, so you can determine with your team that I would rather have a missed prediction than having a false prediction as positive. So, and you can then use that in your pipeline to define a default threshold. In some cases, you can discover that when your confidence threshold is too high, you can actually miss valid predictions or valid detections, and when it's too low, you have many false positives. Again, your use case, your business use case, your team's use case also plays a role along with your data set on determining the best confidence score when you are building this in production. And like I said, for intersection over union, the formula is area of overlap, right? Area of overlap, right? Which is this overlap divided by the area of union. So the IOU means 1.0 means perfect prediction. IOU of 0.5 means YOLO consider this correct, which is map 50, mean absolute precision. IOU of 0.0 means the boxes does not overlap at all. So an IOU of 0.0 could look like this. Let's check this. So it could look like this. Come here again. Have this line again. And have this as a final. So in this case, we have the main box here and we have the predicted box here. This is an IOU of 0.0, which means the detections does not overlap at all. And that is a very, very off prediction. So in our next video, we are going to be discussing, right, about setting this up, right, on our environment, discussing about how neural networks learn, and we are going to be discussing about how to actually put this in code and get it running.